So, welcome. Today is Friday the 17th. Hope you guys are all doing well. Couple things I'd like to talk about before we continue on with material itself today. First, as always, any questions, comments, needs, concerns, please let me know at any time. Interrupt me here, type in the chat, email me, please do that. That's your daily reminder of that. Second thing is our first test will be coming up soon. Namely, it's going to occur during this next week. And it'll be on the first 3 chapters, so we'll take today and Monday to make sure we wrap up chapter 12, make sure everyone is comfortable with it. We'll have a day set aside for review, and around Wednesday, Thursday of next week, I will open up the test for you to be able to take it on WebAssign. Now, when it opens up, that does not mean that you have to take it immediately. My intention would be for us to take a few days of class time, set them aside as instead... Okay, sorry, rewind. I will make the test available to be taken around the midpoint of next week. That does not mean you then need to take it immediately. Once it's up, you can take it whenever you want. Within a few days span, because I do need to make sure that it's in a certain amount of time such that I can actually get everything graded. So around Wednesday of next week, I will open the assignment will become available to you to view. And once it's there, you can open it whenever you're ready for it. After you've had the time to study, after you've had the time to feel comfortable with it, then you can open the assignment, and then it'll begin a 5-hour countdown. Within that 5-hour span of time, you are able to work on the questions, fill in your answers, do all your needed work. It's only designed to take 1 hour. It's only designed to take 1 hour. You just have extra time since it takes longer for you to get test help over the internet. It takes you a longer amount of time to email me your questions. Andrew dropped for a second, so I'm going to reiterate a few points. The test will open up around the midpoint of next week. You can take it anytime you like after it opens. You don't have to take it immediately. Once you feel comfortable for it, once you feel up to the test, and once you've set aside time in your day to do it, then you can open it, and then it starts a 5-hour countdown. You'll have 5 hours to finish a 1-hour test. It's only meant to take 1 hour. It's only 1 hour worth of questions and the math involved. But I'm giving you 5 since it takes longer to get help from me over the internet, and since there's the added step of needing to send me pictures of all your work as well. Once the 5-hour timer is up, that just means that you don't get to enter your answers anymore, and then your grade, I will grade mostly the work that you send me. The WebAssign is just a method by which I know when you access the questions, and it's a method by which your answers are locked in, and then I can check your work separately from them. WebAssign won't tell you a grade once you're done with the test because it's inevitably going to be wrong. Since the way I hand grade assignments is always grade for partial credit first, and then like the last 10% is getting the right final answer. So WebAssign won't show you a score at first for tests. Instead, it'll just leave that blank until I manually fix the score based on the points from your work. So, once the test is available for you to view, you open it when you're ready for it. It's going to open up about midway through next week, and it'll probably be open until through the weekend. You can take it at any time you're comfortable for it. Just set aside the time in your day to do it. If you wanted to, you could take it, say, during class time, and I'll be in here as normal, and you can jump in and out as you have questions. Additionally, I can just be in these calls longer than normal if you schedule with me that you want me to be available during a specific time of day. And my goal was for this to just be as convenient for you as possible. Take it when it's good for you, during the time of day that's good for you, when you're ready for it. To facilitate your test prep needs on WebAssign. Sorry, this is not WebAssign. This is Brightspace. Excuse me. So on Brightspace, thus far in each of the individual chapter tabs, we've had a tab for each chapter. Clicking on the chapter tab itself will open up a list of links to all the video lessons that are useful for that particular chapter, and it also has the note files that I'm teaching from, which you can download and use for yourself. There's also, beneath chapters 10, 11, and 12, a tab dedicated to test number 1. If you click on that tab, it will remind you of all the different categories that will be on test number 1. So this is just the list of all the things we've covered so far that will be on the test. So go over this list to make sure that all of these things are familiar to you. And I have additionally made a practice test that you can just fill out for practice if you want to. It's completely optional. It's just extra questions. Like my past classes have always wanted extra questions that they can use to study. So once you're done with your homework, once you're done with your quizzes as part of your studying, if you want the extra questions to look at to make sure that you are absolutely ready, this is the document you look at. This is just a list of questions that are, if not identical to the test questions, very, very, very similar to the test questions. That they are not identical, but it's a metric of the types of questions you could reasonably expect to see. And if you can do these, you'll be golden on the test. It's completely optional, and if you do work on it, one, you can ask me about the questions, ask me about your work anytime, and there's also separately an answer key so that you can check your math afterwards. I do this for all of my tests, so if you were to scroll down and just take a peek at the Test 2 tab, there is similarly Test 2 practice test and the answer key for Test 2. Same thing for the final exam. All my tests I do this for. So all that material is there for you to be able to use it, in addition to just being able to ask me questions about anything, anytime, especially during the test. I want you to ask me questions about things during the test. Especially if you are misunderstanding a question, if you're not sure what it's asking, talk to me. I will make sure the question makes sense to you, because I want it to be about what you know, I don't want a poorly written question or a question that is written in a way that does not work for your brain to interfere with your ability to take the test. I'm rambling a little bit. Pardon me for that. So, today and Monday will exist for work closing out Chapter 12, making sure everything makes sense, looking at more examples. What I recommend you be doing, over those days and over the weekend is working on all your homework assignments, making sure those make sense, making sure that you have completed them to a satisfactory degree. Once you're done with the homeworks, take the quizzes, make sure you can do those to a satisfying degree. We'll have a few days next week of just review before the test opens, and then the test will open around Wednesday or so. That does mean that the test being open will somewhat overlap with our lab day next week. We will have we will meet for lab next Thursday like we did last Thursday. But again, you have more than one day open to you to take the test. If it opens on Wednesday, you don't have to do it on Wednesday. I'm going to leave it open all through next weekend. The important thing is just open it when you're ready for it, when you have the time set aside for it, and send me your work when you're done. Do your work on scratch paper, send me pictures of it, because that's what I'm going to actually be grading. And I'll send back notes about, what you did wrong, what could be improved for the final exam. So that's all. That's what's coming up in the class. Let me know if there are any questions or issues related to that. If this system does not agree with you or if you have any concerns, I want to know. Please tell me. Additionally, if there's any questions that you have before we look at more examples today, please let me know. I'm going to load up WebAssign real fast. That's not WebAssign, pardon me. I keep doing it again. All right. So, if you don't have any specific questions at this time, we'll continue. We'll continue with our culmination of Chapter 12. We're going to look at some more examples that kind of tie everything into each other, so that you have seen more examples of types of questions that could show up on future assignments and are comfortable with how to work them. The first thing I want to show you guys is actually from the homework, because I honestly think that the way the question is presented in the homework is better than I could draw it quickly, and so I want to show you specifically related to a graphic that's in the homework about something. So hopefully what you should be seeing right now is one of our WebAssign homework questions. And the image currently on screen, this is question 7 on the Chapter 12 assignment. And this image right here, this graph, is a pressure versus volume graph for the specific thermal cycle of a gas involved in, like, the gas inside of a pneumatic cylinder, like some of those examples that we've been looking at. This system right here. So this graph shows the pressure and the volume presently affecting the gas inside of this cylinder. The pressure on it and the volume it presently occupies. The x-axis is the volume and the y-axis is the pressure. And this type of graph is a pretty common visualization that is used to describe the thermodynamic cycle going on for this type of a system. And the different lines on the graph, different points on the graph, represent the different stages of that thermodynamic process. So, if you'll recall from yesterday, we did an example related to this type of a cylinder, where we went through various different stages within its thermodynamic cycle. We looked at the work that it does as it expands, and the work that is required to reset it before it can expand and do work again. Each of these different steps calculated here, the work done on the primary stroke, the work needed to reduce its pressure, the work needed to reduce its volume, the work needed to increase its pressure, and then all those steps added together to determine the total work done by the system. Each of these individual steps is represented by a line on this particular graph here. If you'll recall the formula that we were using, work equals pressure times change in volume. That formula is represented by the lines on this particular graph. We have a volume bar and a pressure bar. So, let's just start with the first step of this cycle. If we start at point A right here, at particular point A, The cylinder is at a specific pressure, 6 times 10 to the 5th pascals, and the step that it takes from point A to point B, we can tell that this is the next step because of the arrow coming out of it. Going from point A to point B, the gas's volume expands from 1 meter cubed to 7 meters cubed. So at constant pressure, our volume expanded. That is, again, the same thing that happened in this first step from our sample question yesterday. A constant pressure as the gas expanded, and that is when the system did work. The gas expanded, the cylinder pushed outwards. So that first step correlates to this line here. The next step is when we reduce the gas's temperature to reduce the pressure of the gas. So at constant volume, the pressure decreases. So we go remaining at 7 meters cubed, we reduce the pressure from 6 times 10 to the 5th pascals to 1 times 10 to the 5th pascals. So the pressure went down, and that again corresponds to the second step right here, where, again, changing pressure is legal, but if the volume is unchanged, there's no work done. So this step corresponds to a work accomplished of 0. Next step, at a constant pressure, we reduce the volume. So work is done on the cylinder. Volume goes from 7 down to 1. And then the last step from D back to A, back to the starting configuration. At constant volume, we increase the pressure again. And as long as volume doesn't change, there's no work done in that step. So these steps correspond to the different amount of work that the gas does or is done on the gas in each part. And this question, when you do it in the Chapter 12 assignment, asks you how much work is done on the gas along each of these paths described during each of the steps. So AB is step 1, BC is step 2, so on and so forth. And again, in step 1, the system will do some amount of work, and then steps 2 and 4, no work is accomplished. Step 3, the work is done on the system instead. Now, describing this process using graphs like this is a pretty common way to represent what is happening here, and using these graphs as a visualization can be kind of convenient, because looking at it this way, we're able to describe our answers in a slightly different way. Let's look again at step A to B. Step AB, that's again where the gas is expanding. The piston is expanding, the pressure is allowing the gas to get bigger, and it's physically doing work as it extends. That work, the formula for that work, is again still pressure times change in volume. And pressure, the current pressure of 6 times 10 to the 5th, times the change in volume, the difference between 1 to 7, our answer is going to be the area under this line. The area under the AB line, all the way from this flat line all the way down to the origin, is the amount of work that this step will accomplish. Because the area under the curve, in order to find that area, you would multiply 6 times 10 to the 5th, the current pressure, times the change in volume, the distance moved along the x-axis, which again, you end at 7, you begin at 1, so that's a difference of 6. The area under the curve for this graph is the pressure times the change in volume. So this graph is literally just directly a visualization of this formula. Work equals pressure times change in volume. That graph is this formula turned into a picture. And on this graph, it's easier to see why these two steps, where the volume remains constant, don't have no amount of work being done. Because when the volume remains constant, there's no area under the curve. It's a flat line pointing downwards or upwards. There's no area under that. There's no area under BC. There's no area under AD. It's just an infinitesimally flat line. Which is why if you again look at the answers down here, step B and step D have a work accomplished of 0. No work is done on it, no work is done by it, because there's no area under that curve there, since the formula requires a change in volume, a scrolling along the x-axis. Meanwhile, for the third step, going from point C to point D, there is an area under this curve. It would be 1 times 10 to the 5th times, again, scrolling from 7 to 1. That would give you an answer of the opposite sign as our first answer. Because our first answer was 6 times 7 minus 1. This time around, it's 1 times 1 minus 7. So our first answer, our first area is a positive area, whereas our second area is technically a negative area because it's scrolling backwards. It's the x-axis would actually give you the change in the x-axis gives you a negative number that time. So they are two different areas, but one of them is technically negative, which is a weird thing to have to visualize. What that means is, since this area is technically negative, and since it overlaps with the bigger positive area of the first step, that's why when you add all the steps together, one of the steps, like the first step is the gas doing work, the second step is work being done on the gas. That's why those two numbers work against one another. That's why the lump sum is a smaller number. Like, it's not the two added together, it's the two subtracted from one another. Like, again, with our example yesterday. Step 1, the gas does work outwards. Step 3, the gas has work done inwards on it. To figure out the total lump sum of energy flow into or out of this particular thing, positive plus a negative gives you a slightly smaller answer. And again, this is just the visualization as to why that happens. Now, I do want to... I will go ahead and acknowledge that for this particular question, for question 7 on the assignment, this is a very good picture. The answers might have an opposite sign as one might expect, and that's because the question asks for the work done on the gas. It wants the work done on the gas. And technically, step A to B is work being done by the gas. So that kind of inverts the perspective. If the gas is doing work, it's sending energy out of itself. So in this case, if it was doing work, it'd be a positive answer. It is doing work. And if we wanted to know, well, how much work is the piston doing, that would be a positive number. But WebAssign is asking this one from the perspective of work done upon the gas. And from that perspective, the gas doing work would be opposite. So if the piston does work, it does positive work out, but that means that that negative work is done. It's as if negative work was being done on it. It's a weird technicality due to the fact that you could ask this question from two different perspectives. Either work is done by the gas and it's sending more energy out of itself, or work is done on the gas and energy is being added. It's a matter of perspective, and so for this question and for similar ones, it's important to read the asked for perspective within the question. Either work done on or work done by the gas. And since in this question it's work done on the gas, that kind of reverses the signs you would expect on all of the answers. Again, this is a super common way to visualize this data. In fact, there's a different question in this homework, question 3, that shows some similar visualizations, and you have to pick which one is the most accurate for the rest of the question described here. So, common way to show the data for that type of a question. Wanted to make sure you'd seen that. Questions, comments, needs, concerns, please let me know. Excuse me. Okay. If there's no issues regarding that just yet, then let's continue looking at the chapter 12 notes. What we're now going to do is look at some more example questions that are intended to tie various laws of thermodynamics and other principles into each other. We're going to start again. Yesterday we kind of concluded by looking at the second and third laws of thermodynamics a little bit closely. We're going to pick up there where we left off. As a brief refresher, the second law of thermodynamics is the law of entropy. It's the law that says all processes either create... If a process is completely frictionless, it doesn't create any new thermal energy, and the net entropy change of the universe will remain zero. But all real processes, everything that you can actually physically do in the universe that is irreversible, that happens naturally, involves some amount of friction, some amount of thermal energy will be created, and that increase of thermal energy slowly increases the entropy, the chaos level of the universe. This is the law that our efficiency formula is actually derived from, because again, efficiency represents how much work a machine can do based on the amount of energy that it was given. If, hypothetically, a machine was 100% efficient, then all the energy fed into it would be used as work. That would be a 100% reversible process, and no new thermal energy would be created. If you put a, 1 megajoule of gas into your car, a 100% car could turn all of that into 100 megajoules of kinetic energy to get you ready to go. 100% efficient machines wouldn't increase entropy. However, all real machines have some amount of friction. All real machines are some degree efficient less than 100. In fact, most physical apparati, and that includes organic life forms, because they are, in a way, just machines made out of carbon and such, in terms of the physical motion of those organic creatures. All of those things that can move have some degree of efficiency less than 100 because of friction. And in reality, most things... At times, you're kind of lucky if you're getting an efficiency of 5%. I think the human body is routinely cited as 20% mechanically efficient, which is, again, really good. In nature, you rarely find anything more efficient than that. I think some of the most efficient, high-performance machines that you can get designed for scientific settings to minimize friction as much as possible are still only 50% efficient. If you could invent a machine that was 90% efficient, you'd probably win a Nobel Prize. If something was hypothetically 100% efficient, then you will have basically discovered perpetual motion. The idea that a machine can keep running based on the amount of energy you already gave it because it never loses any energy. It can just... The energy stays in the machine in a mechanical form, and it can continuously be used to continue moving. Like a Ferris wheel that never stops. It never slows down. It never speeds up. It can just continue without any energy being added to it. That's, if you've heard the term perpetual motion before, that's what it's referring to. And it's, again, impossible because of friction. So, this is the law where we get our efficiency formula for, and I'm going to tab over to that formula real fast. So, thermal efficiency. If, again, you had a 20% efficient machine, the output would be 20, and the input would be 100. So the efficiency is the output the output divided by the input. And for different machines, those different variables might be called different things. For the human body, the input is the food that you eat, and the output is the physical work that you can accomplish. For a car, the input is the amount of gas you put into the car, the energy inside of the gas you put in the car, and the output is the actual amount of work the engine can accomplish to make your car move forwards or backwards. There's also some devices that are referred to as heat engines, or sometimes heat sinks, that operate based on pulling in thermal energy to do a certain amount of tasks and then sending excess thermal energy away, pulling energy between hot and cold reservoirs. This would be like what happens inside of your refrigerator. The purpose of a refrigerator is to pull heat out of the inside of the fridge and send it outside. So you're pulling heat out of a cold reservoir and sending it to a hot reservoir. And the efficiency is the function of how much energy do you pull out versus how much energy do you then vent outwards. So the efficiency formula can be used to describe how effective a machine is, and that what the input versus output is called will depend on what the machine is. Might depend on a few different variables. And I'd like to start looking now at some general examples that include an efficiency component to kind of show a few of the different ways that it can manifest, a few of the different ways it can be described. And to, again, try to tie together the various things we've been... Oh, no. How long was I gone? It makes a noise when I pop back in. It makes a noise when you guys pop in and out. But it doesn't make a noise when I lose signal. So I just keep talking if I'm not actively on the screen that shows me the call. So...
You were gone for a good while.
Ah, yikes. Thank you for telling me. Sorry. Let's put the PowerPoint back up. Pardon me while I get resituated. Have to reset a few things after the call boots me in and out. Okay, so let me try to go back over the important part. Second law of thermodynamics, just as review, this is the law that tells us about entropy and chaos. Every process turns, because of friction, every process, every motion turns some amount of energy into thermal. As a result, that increases the total entropy of the universe. The only type of process that hypothetically wouldn't create new thermal energy is one that is 100% efficient. If you had a machine that was 100% efficient, all the energy in became work output. Excuse me. That would be 100% efficient, and hypothetically, that wouldn't increase entropy. But in the real world, most machines you'll encounter are anywhere from like 5 to 20% mechanically efficient. And that includes the motion of organic creatures as well. I keep hearing the statistic that the human body is about 20% mechanically efficient. I will have to research that statement further, but it's data I keep being given. If you hypothetically invented a 100% efficient machine, you'd win a Nobel Prize if you invented a 90% efficient machine. If you invented a 100% efficient machine, that would be perpetual motion, and you would either have won a Nobel Prize or you would have broken physics. So, if either of you accidentally discover that, let me know. So, this is the law that we get our efficiency math from. The efficiency formula is, once again, nth equals the machine's output divided by its input. Once again, yikes. keep losing signal today. It's becoming a real problem. Oh, I'm annoyed that that keeps happening.
Maybe it's a sign.
Maybe it's a sign for everyone to take a nap.
Yeah.
Hmm.
It is Friday after all.
It is Friday after all. All right. Three's the magic number. So if it happens one more time, I'll have to try to keep a better eye physically on this window. Okay. So, second law of thermodynamics is what informs our efficiency math, our efficiency equation here. It is Friday, so I definitely don't want to keep you. But I do want to at least show you one or two things before the weekend. Machine's output divided by its input will tell you how efficient that machine is. Exactly what the output and input is called might depend on the machine itself. For example, the human body, the input is the food you eat, and the output is the mechanical work that your muscles are able to do. For a car, input is gas, output is the work of the engine. For a refrigerator, as a specific weird example, what that machine is designed to do is take thermal energy out of the cold part and send it out the coils on the back of the machine out into, the rest of the universe. So in that situation, the input is the amount of energy needed to accomplish that task, and the output is the energy that it's able to send out from the back. So what is input, what is output will depend on the question, and that's why I want to show you a few different examples. Looks like I'm not the only one losing signal today. Okay. So, straightforward example, just to illustrate the basics of how this is applied. Let's say that you add 100 joules of thermal energy into a pneumatic cylinder. We know its pressure, we know its change in volume as a result of this thermal energy being added to it. What is the efficiency of this particular system? So we know the input, we need to calculate its output. We know the amount of energy we put into it, we need to know how much work it was able to do from that input. So for this particular cylinder, we know its pressure and we know how its volume increases. So we can use work equals pressure times change in volume, constant pressure of 25 pascals, change in volume from 2 to 5 meters cubed. Again, if you plug in pascals and meters cubed, that will give you final units of joules. You don't have to adjust anything. So 25 times 3, this machine does 75 joules of work in this particular action. So we gave it 100 joules to do that 75 joules of work. That makes this machine 75% efficient, which again is actually really, really good. That also means that there's 25 joules of energy just kind of uselessly kicking around inside the gas, inside the metal of the cylinder, accomplishing no task other than just making the cylinder hot. And in order to reset the cylinder to get it to do more work, you have to, again, remove all that thermal energy to reset it and then begin the cycle anew. second example related to this. I want to use this to kind of demonstrate how inefficient fire is. Fire as a process, as a method by which humans harness energy, is actually really bad. Not just for the environment, but in terms of like the energy conversion involved. So 1 kilogram of coal contains 24 megajoules of energy. If you burn 1 kilogram of coal in order to melt 200 grams of ice, what is the efficiency of this process? So, in order to melt ice, we have to consult Q equals ml, because melting is a phase change. Our mass of ice is 200 grams, which will convert to 0.2 kilograms. We also need the latent heat of fusion for water. And since this is either solid to liquid or solid to liquid or liquid to solid, we need specifically fusion as the value we want to pull from the table. Latent heat of fusion for H2O is 3.33 times 10 to the fifth. And so those two numbers multiplied together tell us that we need 66,600 joules of thermal energy to melt this ice. If we burn 1 kilogram of coal to accomplish that, oh geez, I did my math wrong here. I don't know why, but I did my math wrong. I said 24 megajoules of energy, but I only wrote 1 megajoule of energy. That's my mistake. Which means that this process is actually even worse than I thought. Even worse than I thought. So the math I show here, our output is the goal that we wanted to accomplish. We wanted to melt the ice. So the output of our setup, the actual thing that our setup is accomplishing, is melting this ice. And that task takes this much energy. So that would be the hypothetical output of our process. For input, that would be the amount of energy you put into the fire. And what I have here, just 1 million joules, is actually only 1/24th of 1 kilogram of coal. So I suppose the question is now actually, if you had 1/24th a kilogram of coal and it gave off this much energy, what would the efficiency of that process be? My mistake there. I apologize. I don't know why I didn't catch that. Oh, I've lost my network connection. I can tell this time. Hello. It told me I lost connection. Oh, there it is again. It made the sound, but it's still saying that I've lost signal, so that's conflicting information. It says ugh. Gotta love technology. That was like me losing signal 3 times in a row, so that seems to be the indication that you hinted at earlier, that we're probably done for the day. So I'll just wrap this one up and then we can call it. Just the last point that I wanted to make here, and again, even my wrong math demonstrates this to some degree. I didn't even use the whole kilogram of coal, and this process wound up like 7% efficient. Fire is notoriously inefficient because you don't just heat what's above the fire, you heat the surroundings of the fire, you heat all the air rising up past the fire, And those cinders, that the burning coals left over afterwards, will continue venting extra thermal energy into their environment until they are completely put out. So, fire is really inefficient, and unfortunately, all cars, all coal and oil burning power plants still utilize fire and therefore are horribly inefficient, and we need better solutions. And I say we probably wrap this up before I lose service again. So, there's one or two more things, that just more samples that we can look at on Monday. But you're right, it's Friday and my internet is being super wobbly right now. So, I'll do my best to stick around for the next hour for as long as my signal lets me. If you have any questions, needs, concerns, etc., pop back in over the next hour or email me over the weekend. Be working on Chapter 12 and previous homework assignments. Make sure you're satisfied with those before we move into test prep season. And I literally lost signal mid-sentence again. Have a nice day.